recording starts. So we talked about the source-free RC circuit on Wednesday, right? Do you remember to solve this type of circuits? We have this equation, right? So this is the capacitor voltage equals the VO is the initial voltage of the capacitor times E, the exponential term, and negative T over tau. So for this circuit, we need to calculate VO and the tau. Once we have the value for VO and the tau, we plug in the numbers and we obtain the voltage, the capacitor voltage. We have the expression for capacitor voltage. Similarly, today we will discuss RL circuit. For RC circuit, we calculate the capacitor voltage, and because the capacitor voltage cannot have instantaneous change. Here in RL circuit, we calculate the inductor current because the inductor current cannot have instantaneous change. So for the RC circuit, for the capacitor voltage, we have this equation. Similarly, for RL circuit, for the inductor current, we have this equation. But the tau, the definition of tau is different. For RC circuit, the tau equals R times C. For RL circuit, the tau is different, and we will discuss tau today. And also similarly, in RC circuit, this is VO, the initial voltage of the capacitor. For RL circuit, here is the initial current of the inductor, and we will use some examples today. So let's start. Source-free RL circuit. Similarly, the source-free RL circuit, it does not have a power supply. The circuit is excited by the energy stored in the capacitor. It's stored in the inductor. So the inductor has the initial current I, and similarly to the this is the initial current I0, and it will exponentially decay to 0 because the resistor will consume the energy. So here we assume that the initial current is I0. So we have the initial energy stored in the inductor, use this equation. And finally, this energy will be consumed by the resistor. And we can apply KVL in this circuit. That is the voltage on the inductor plus the voltage on the resistor equals 0. That is VL plus VR equals 0. From the definition of inductor voltage, we have the VL equals L didt. VR equals I times R. So we can plug in these two equations into this equation. This is the first order differential equation. It's very similar to the source-free RC circuit. And then we do some math and integrate both sides. And finally, we get this expression. So this expression is for the inductor current. Here, the I0 is the initial current of the inductor. Here we have the T, but here is the L over R. So the tau here is R, L over R. So the inductor current can be written in this expression. The I/O times E negative T over tau. But the tau here is L over R, not R times C. In RC circuit, it's R times C. But for RL circuit, it's L over R. And that's the RL circuit. So once you obtain this one, we can do some exercise. Oh, so this is the current. So it's also exponentially decay. Remember the RC circuit, the source free RC circuit. The capacitor voltage is exponentially decay. But in this circuit, the current is exponentially decay. And using tau is called the time constant. After 1 tau, the current is decreased to 36.8% of the initial current. And usually after 5 tau, we think this current is decreased to 0. So that the smaller the time constant tau of a circuit, the faster the rate of decay of the response. So if the tau is smaller, so the slope will be larger, so faster decay the current. The larger the time constant, the slower the rate of decay of the response. And that's the RL circuit. So for the energy, so all the energy, the initial energy is stored in the inductor, and then as time goes on, the energy is consumed by the resistor. So the key to working with a source-free RL circuit is first, we need to find the initial current through the inductor. So sometimes the initial current is given directly, but sometimes the initial current is not given directly, but give you a circuit and tell you the switch closes or operates at time 0. So you need to calculate the inductor current before the switch open or close. That is the inductor current when T is less than 0. Assume steady state. In steady state, we treat the inductor as short circuit or open circuit. In steady state, we treat
Short circuit.
yes,
Yes.
short circuit. And how about capacitor?
Open.
Okay,
Yep.
that's right. So we treat the in DC steady state, we treat the inductor as short circuit and capacitor as open circuit, and use KCL, KVL, loop analysis or mesh analysis to calculate the initial voltage of the capacitor or the initial current of the initial voltage of the capacitor or initial current of the inductor. Later we will use an example. And then the time constant of the circuit. So in previous lecture, we learned how to calculate the time constant of RC circuit.
Yeah.
Right. So for RC circuit, this equals the R PQ times C, because there might be multiple resistors in this one. For the RL circuit, we have this one, but here we may also have multiple resistors. So this is REQ over R. Typically, we have one inductor. So let's use an example. Oh, and with the two items, we obtain the response as the inductor current, so IL. Once we determine the inductor current, other variables, for example, the inductor voltage, resistor voltage, and resistor current can be obtained. Note that in general, R in the previous equation is the several resistance at the terminals of the inductor. So use an example. So maybe give you some time to solve by yourself, and then we discuss together. maybe 5 minutes to work on this example. Should you not near the analysis? Because when the switch is closed, right? So this one is short circuit. So this one has been short circuit. We can remove this. So this resistor and this resistor, they are parallel in series.
Greater equivalent resistance, where do you try to find that? Because I did it, release 3.
Yes, yes.
So these two would be series, right?
Look, so these two series and then this becomes 16. So so when the switch is open.
Yeah.
So this one does not exist.
Oh, okay.
Yeah.
I can see that.
So this in series and then parallel.
Gotcha, okay, I did that backwards, so.
So let's take a look together. So when t is less than 0, so this switch is closed. And in DC steady state, that resistor will use a short circuit. Right. So here is short circuit. Short circuit. So this 16 ohm is in parallel with the short circuit. So this has been short circuit. So the current will flow through this branch and will not flow on this resistor. So this resistor we can remove it. So the circuit looks like this. This two, this 12 and 4, they are parallel. And then in series with this two. Right. So the 12 and 4 parallel will obtain the equivalent resistance 3. And then the 3 in series with this 2 is 5 ohm. So we calculate the current I1, that is 40 over 2 plus 3. So this is I1. And using the current division, because we know the value for these two resistance. So the current IT, that is the current flowing through this 4 ohm resistor equals the 12 over 12 plus 4 times I1. This is the current division. So this becomes 6 ampere. So the current when T is less than 0, the current flowing through the inductor is 6 ampere. And we know that the inductor current cannot have instantaneous change, so that we have the initial current for the inductor. Next, when T equals 0, the switch is open. So this voltage source and this resistor do not exist in this circuit. So we replot the circuit. So in this circuit, we have the 12 4 ohm resistor. So the 12 and 4, they are in series. And then becomes 16, it becomes 16, and then parallel with this 16. So the R equivalent equals 8 ohm. So we have the value for L and we have the value for R. So we can calculate the tau equals R, L over R. So this is 1 over 4 seconds. And we plug in the equation. The 6 is the initial current. And T over negative 40. That's the inductor current.
Go over one more time, I mean,
Oh.
the initial current.
Initial
is
current.
6 amps.
Okay, no problem.
Yeah.
Yeah. So here is, so when T is less than 0,
Yep.
we have this circuit. So the inductor is here, right? We treat this as short circuit. Right? So what we need to calculate is this circuit, I1. Okay. So this 12 and the 4, they are parallel, correct? So we obtain the equivalent resistance, which is 3 ohm.
Gotcha.
So our circuit can simplify into this. This is 2, and this is 3, right?
Quick question, why does the 16 ohms go away? Or like, why don't you use that?
Yes, the 16, this 16 go away because this is short circuit.
Okay.
So this resistor has been short circuit.
Okay,
So no current will flow.
Gotcha.
on this resistor.
Okay. that makes sense.
So then we have the 2 ohm, 3
Yeah.
ohm. That is the current 8 ohm. So this is 8 ampere, and use the current division. So 12 and 4, the current division. So we obtain that the I1 equals 6 ampere.
makes sense.
Make sense? Yeah. No problem, right? Okay, let's have one more example. Yeah, now I have the solutions on my slides. Yeah, so you can check the solutions. So the next one is in the circuit, find I, O, V, O, and I for all time, assuming that the switch was open for a long time. And then at time equals 0, the switch is closed. So before time 0, the switch was open, and at time 0, the switch is closed. So take a look at this one. one suggestion is that the circuit is given that I suggest you plot the circuit when the switch is closed and the plot the circuit when the switch is open. So you can get two circuits. Do not work on the original circuit. Both two separate circuits. When the switch is closed. Good. Yeah, sure. So for the first one, I said you have no problem. When T is less than 0, the switch is open. So this branch does not. And in steady state, the short circuit the resistor. So this 6 resistor has been short circuit. So we remove it. No current flows. So 2 and 3 in series. This is 10. So we have the current. Yes, I0 equals the I0 plus because the battery current cannot have instantaneous change equals 2 ampere. So finished 50%. And then another 50% is that when T is greater than 0, because this is has been short circuit. So this you have this one, right? So the switch here is closed. So the switch is closed. So the current will flow here. So this becomes a separate circuit. It does not influence the right side of the circuit. So let's calculate the equivalent resistance of the right side of the circuit. We have a 3 and 6 in parallel. So the Req equals 2. And we calculate tau. 1 second. Plug in the initial value of the current and plug in tau. We have the expression for IT. And once we have the current on the inductor, we can calculate the voltage on the inductor, L di dt. And because that here is VO, this is VL. So VO equals the negative of VL. So VL, we have this relationship L di dt. We can obtain the VO. And calculate the I0 I0. So this I, so the current on this resistor, because we calculated the I, we can obtain the voltage on the inductor that is L times dI/dt. So this 6 ohm resistor is in parallel with this 2 Henry inductor. So the voltage is the same. So use Ohm's law, we can calculate. So we have the, so here we have the VL, that is the voltage on the inductor L dI/dt. Because the 6 ohm resistor is in parallel with this inductor, so the voltage on the 6 ohm resistor is the same as the voltage on the inductor. So this current on the 6 ohm, so this equals 6 ohm. So it's very similar to RC circuit, but the only difference is that you need to find the initial current and also the top. For the RC circuit, you find the initial voltage that you need. So that's the only difference. You can, yeah, plotted the solutions. But here you can see that the inductor current cannot have instantaneous change, but this is the resistor current. Resistor current can have the instantaneous change. And you see it jumps from 0 to the negative 2/3. This is the inductor current. But this is a resistor current. But the inductor current cannot have instantaneous change. So yeah, take a look at this example. Close book. Yeah, when you go back home and close the solutions and do it yourself. I added the solutions. So the next one is we have 10 more minutes, right? Okay. Singularity function. We will introduce 3 singularity functions. So so singularity functions are functions that are either discontinuous or have discontinuous derivatives. And we will introduce the 3 most widely used singularity functions in circuit analysis. That is the unit step, the unit impulse, and the unit ramp. So the unit step function, UT, we use UT to denote the unit step function. So this function is 0 for negative values of t and 1 for positive values of t. So this function, when t is less than 0, it's 0. When t is greater than 0, this is 1. So this is unit step. Why we call it unit step? Because it looks like a step. And the value is 1, so we call it unit step. And the unit step function is defined when at t equals 0, where it changes abruptly from 0 to 1. And it is dimensionless, like other mathematical functions, like sine or cosine. We can move left or right. For example, we can move the function from the 0 to time t. So this becomes t minus t0. So this becomes that when t is less than t0, the value is 0. When t is greater than t0, this is the value is 1. We can move left or right. We can also move left. So this is the unit step function. we use the step function to represent an abrupt change in voltage or current, like the changes that occur in circuits of control system and digital computers. For example, the voltage, if we have the voltage when t is less than t0, the value is 0. The t is greater than t0, the value is 0. So we can use this unit step function to represent the more complicated. So this Vt equals 0. This is amplitude because the amplitude of the unit step function is 1. So, but here we need to express the magnitude of amplitude of V0. So we multiply V0. And also here the t is not 0, it's t0. So we move the unit step function to express this Vt. So the VO times UT represents this case that when the these two are equivalent. These two are equivalent. When t equals 0, we put the VO into the circuit. So this equals the VO times UT. And also for the current, when t equals 0, we close this switch, so the current is flowing in this circuit. And this is equivalent to I0 times Vt. So this is when t is less than 0, it is open circuit because the current source is not in the circuit. When t is greater than 0, the value is I0, that is IT. We put the source in the circuit. And the derivative of the unit step function ut is the unit impulse function, where we write as. So this is the derivative of the unit step function. So remember the unit step function. So this is a unit step function, right? At time t, it has abrupt change. And when t is less than 0, the value is 0. When t is greater than 0, the value is 1. But they are constant. So we take the derivative of the unit step function so that when time is less than 0, this value is 0 because it's a constant. And when t is greater than 0, because this is a constant 1, so the derivative is also 0. But here at time 0, it has abrupt change. So we take the derivative. So here the derivative is undefined. So that is the unit impulse function. So the unit impulse function is 0 anywhere except t0, where it is undefined. So it is 0 anywhere except t equals 0. At time t0, this function is not defined. The value of this function is not defined. But the integration of this function, the unit impulse may be regarded as an applied or resulting shock. It may be visually as a very short duration pulse of unit area. This may be expressed mathematically as this one. Even though this value is not defined at time t, but the integration of this function in a very tiny time interval is 1. And we can also multiply the coefficient to express the amplitude. And next, we will introduce the sampling of a function. So that is this one. So let's assume that ft is another function. It's a random function. So this delta is the impulse function. So we have two functions multiplied together. So this is ft. It can be any continuous function. And we have the delta t here. We assume here is t0. So this is delta t minus t0. When these two functions multiply together, we see that this function, the unit impulse function, is 0 except when t equals 0. So that this integration, so this multiply this equals the ft0 times this unit impulse function. Because when t is not equal to 0, all other values equals 0. So this 2 equals this one. And because this is a constant, so we move this out of the integration. It becomes this. And this integration is 1. So finally, this equals 1. So we call it this is the sample characteristic of unit impulse function. So this characteristic will not be used in this course, but in future engineering course, in signal and systems, we will discuss more details about these characteristics. So you don't need to master this. Yeah. So so this slides, you only need to know you have this, but if you cannot understand the details, it is fine. It is okay. So let's continue. And the next is the integrating the unit step functions. So integrate this unit step. So it becomes this unit ramp function. I think that's all for this one. So their relationship is that you integrate the unit step, you get you integrate the unit impulse, you get the unit step, and you integrate the unit step, you get the unit ramp. That's the relationship. That's all for today. Yeah, that's all for today. Stop recording.